Hello friends, today we're going to discuss the topic of calculation of magnetomotive force and magnetizing current of three-phase induction motor. When three-phase AC supply is given to the induction motor, it sets up a magnetic flux. This magnetic flux is set up through the stator core, stator teeth, air gap, rotor teeth and rotor core, and the flux completes its path. So the magnetizing component of the no load current, which is responsible for setting up the flux, will be providing the flux, and it will require large amount of mmf to set up this flux due to the fact that there is a air gap in the circuit, and this air gap has got large value of reluctance. So the mmf of three-phase induction motor basically consists of the air gap reluctance, stator teeth reluctance, stator core reluctance, stator rotor teeth reluctance, rotor core, and also this mmf is also affected by this saturation and if there is a radial ventilating duct present in the induction motor. So let's understand how this magnetomotive force can be calculated, and from there we can calculate the magnetizing component of no load current of three-phase induction motor. The mmf required for the air gap is given as the product of flux density into the length, because we know that mmf is nothing but the amount of force required to set up the flux in the magnetic path. Here Lg is the length of the air gap, Bg 60 is nothing but the flux density at 60 degrees from the interpole axis, and Kg is the factor for the air gap. So this Bg60 is the flux density at 60 degrees from interpole axis. This is due to the fact that the AC system basically consists of large amount of harmonics. The harmonics which is of the third order basically is more predominant as compared to the other order harmonics. So if the fundamental frequency flux and the third harmonic flux, if they are added, we will get the actual flux density curve, which is more flattened rather than having a sinusoidal path. So in order to take into consideration the third harmonic component into the magnetic flux, we generally take the flux density at 60 degrees from the interpolar axis. This is because the flux basically is getting distorted. So the magnetomotive force of the air gap is generally the product of 800,000. This is nothing 1 upon 4 pi, which is nothing but the value of mu 0. And then since this is an air gap, we know that the relative permeability of the air gap will be mu r will be equal to 1. So here we are able to calculate the magnetomotive force of the air gap. Next is the magnetomotive force required for the stator teeth, that is given by ATS. Usually the slots in the three-phase induction motor are tapered. Hence the flux density throughout the teeth does not remain the same. So what we do is we take into consideration the flux density at 1/3 the width of the stator tooth, that is 1/3 of the height from the narrow end. So therefore we can calculate the value of flux density at the tooth, which is at 1/3 the distance, as P phi m upon SS Li WTS 1/3, where WTS 1/3 is the width of the stator tooth at 1/3 height from the narrow end. This value we can calculate by taking into consideration the stator bore diameter, the depth of the stator slot, and the width of the stator slot, and of course the number of stator slots. So here we are taking into consideration the value of the flux density at 1/3 distance. Once we know this value of the flux density, then for the given material which we are using for our stator core, we can obtain the ampere turns per meter from the BH curve, that is nothing but the BH curve of the material which we are going to use. So once we know the ampere turns per meter of that material, for that given flux density, we can calculate the total MMF required for the stator tooth as the product of ampere turns per meter into the depth of the stator slot. So this will give us the value of the magnetomotive force required for the stator tooth. Similarly, we can also calculate the magnetomotive force for the stator core, because stator core is uses the same material as the stator tooth. So here also we are going to calculate the magnetomotive force required for the stator core as the ampere turns per meter for the stator core material into the length of the stator core, where length of the stator core we are considering the formula pi d plus 2 ds plus dcs upon 3p, where we are taking this depth of the stator slot and the depth of the stator core, and p is the number of poles, d is nothing but the stator bore diameter. So here we can calculate the value of MMF for the stator core. Magnetomotive force required for the rotor teeth is calculated in the same way as we have calculated the magnetomotive force for the stator teeth. So for rotor teeth we are considering here, again assuming that the rotor teeth rotor slots are also tapered, and we are considering the width of the rotor slot at 1/3 height from the narrow end, and we are considered for the stator, we are also considering here for the rotor. So we are calculating the width, because again why this is important is because the flux density will be maximum at that particular place, and once we know the maximum flux density at that 1/3 distance, we can again choose the material, and from the BH curve of that material we can calculate the ampere turns per meter. Now here not necessarily that the core material used for the rotor and stator may be same. If they are same, we can choose the same ampere turns per meter, but if they are different, then the ampere turns per meter for the rotor core material will be selected, and its BH curve will be taken into consideration. The magnetomotive force required for the rotor tooth therefore will be ampere turns, TR is given by ampere turns per meter into the depth of the rotor slot. So by taking into consideration the depth of the rotor slot, we can calculate the value of ampere turns required for the rotor teeth, that is nothing but MMF. And finally, we can calculate the magnetomotive force for the rotor core similar to the ones we have calculated for the stator core. Here we are from the BH curve, again from the material we can calculate the magnetomotive force per meter, that is ampere turns per meter, and then we multiply it by the rotor core length. Now generally we know that rotor core length is same as the stator core length, but if in case for exception if they are different, then we can use this particular formula to calculate the length of the rotor core. Then finally, once we obtain all these magnetomotive force can be calculated, that is known as the total magnetizing pole for B 60 degrees is ampere turns 60. So 80/60 is generally the sum of the ampere turns for the air gap, ampere turns for the stator core, ampere turns for the stator rotor tooth, ampere turns for the stator core, and ampere turns for the rotor core. So once we get the ampere turns, total ampere turns, then we can calculate the value of magnetizing current by the formula as 0.427 into P ampere turns for 60 upon kW into TH. So that it is only depicting that the ampere turns is nothing but the product of I into turns, number of turns, and all this since we are taking into consideration the P. Here we have calculated the average magnetomotive force, so we take into consideration this factor of 0.427. So definitely we are able to calculate the magnetizing current for the three-phase induction motor. Now this magnetomotive force or the magnetizing current also gets affected by the saturation. So if the magnetic flux in the induction motor saturates, then definitely there will be an effect which will be there on the magnetizing current, because finally it is going to affect the magnetomotive force. So the leakage coefficient is nothing but the ratio of total flux to the useful flux. The area of tooth, if it is small, it is likely to have a saturation. So the thickness of the tooth which we are taking at 1/3 the distance, if that 1/3 distance is very small, width of the tooth is very small, then it is like most likely that the saturation will occur at that particular point. So then in that case we will have to increase the value of leakage coefficient, and increasing the value of leakage coefficient will lead to increase in the value of the magnetomotive force required for the tooth, and then hence the total magnetomotive force 80/60 will also be increased, and this will increase the magnetizing current. So the effect of saturation is that saturation usually leads to increase in the magnetizing current, and then if the magnetizing current increases, definitely we know that the no load current will also increase, and motor will draw very high current during starting even under no load condition. So saturation is going to affect the starting performance of the three-phase induction motor in sense that it is going starting current drawn will be very high. Same type of effect can be observed if we have a duct in our stator of three-phase induction motor. Generally, it is there is a thumb rule which says that a radial ventilating duct of 8 to 10 mm, here I am assuming it is 10 mm, is required after every 100 mm length of the core in both stator as well as the rotor. So definitely the duct which is the radial ventilating ducts will increase the total length of the core. So here the total length of the core due to the radial ventilating ducts will be the rotor or stator core length plus the Carter coefficient into the number of duct into the width of the duct. So if the number of if I assume that the width of the or length of the core is, let's say 300 mm, so I will require minimum 2 ducts with 10 mm thickness. So definitely the duct will increase the overall length of the motor. Not only that, it will also increase the leakage coefficient. We know that if the duct is there, definitely there is a property of the magnetic flux to bulge out. So definitely this flux will bulge out, and then this Carter coefficient will come into the play, and we will have to multiply that particular Carter coefficient due to the bulging into the length. Hence, if the length increases, then the total MMF required for the motor will increase. That increases the magnetizing current. So magnetizing current increases both due to saturation as well as the ducts. Thank you.